Hello and welcome to today's webcast titled Overcoming CCR Challenges, Solutions for Ash Pond Wastewaters. I'm Aaron Larson, Executive Editor of Power Magazine, and I'll be hosting today's program, during which we'll hear from Max Swoboda and Charles McCloskey. Max has 25 years of experience providing technical and water treatment solutions to power plants. He has developed solutions ranging from ultra-pure water production to water treatment services for fossil and nuclear facilities. Max joined Evoqua in 2016, focusing on wastewater needs of power plants, particularly coal-fired plants that need to stay in compliance with CCR and ELG regulations. Charles has more than 40 years of experience developing industrial water and wastewater treatment solutions. During his stint with Evoqua Water Technologies, he has been the marketing manager for Power and the director of industrial wastewater projects. He has held positions in technical service, sales, product management, and general management throughout his career. Today's presentation is expected to last about 25 to 30 minutes and will be followed by a Q&A session. Before we get started, I'd like to run through a few housekeeping items. On the lower left-hand side of your screen, you should see an area where you can type and submit questions to the speakers. Feel free to send in questions at any time during the presentation, and we will try to answer as many as possible during the Q&A portion or via email after the program. If you are experiencing any technical difficulty, you can ask for help by typing the problem in the same area on the lower left of your screen, and our production staff will assist you. The program will be available for download, and you can access a PDF of the slides under Event Resources at any time via the live studio link. It will be archived on our server, and future viewing will remain free of charge. You can use the same URL to reach the archived program as you did to reach the live program. A certificate of completion for professional development hours will be sent out via email to every registered participant who attends. Before we begin, we would like to thank Evoqua Water Technologies for underwriting today's program. The company's generosity allows everyone to attend the presentation at no cost. And with that, I'll turn the program over to our first speaker, Max Swoboda. Max, take it away.
Hello and welcome everyone. Today I'll take 10 to 15 minutes to step through some typical ash pond closure design items and case studies. Then Charles will take over for another 10 to 15 minutes to discuss life after ash ponds and what a future plant water balance looks like. He will also explore one resulting issue in depth, non-chemical boiler cleaning wastewaters. Since the calendar has rolled over to 2018, we are already a number of years into compliance with CCR regulations. The next set of pending deadlines starts to come into play towards the end of 2018 and 2019. During this time, many source waters will be diverted from CCR impoundments and will require treatment systems to close the impoundment. Being less than 1 year away, the deadline is generating interest in temporary treatment systems while plans and construction of permanent systems are ongoing. Concurrently, groundwater monitoring and systems for corrective actions are also anticipated. That brings us to our poll question here. How will these key dates for your CCR and ELG regulations affect when you need to stop using your ash pond?
All right, the responses that are available here are my plant will stop using our ash pond effective January 1 of 2019. Or we'll continue using our ash pond beyond January of 2019. My plant's ash pond closure is in process or already closed. Or I'm not at a plant with an ash pond. And you can begin answering at any time. We've got quite a few responses already in. Looks like we've got a lot of webinar attendees who don't work at plants with ash ponds, but there are split pretty evenly among the others that are still using or will stop using by 2019. We'll give you guys a little bit more time to answer the question and send out the results. All right, Max, I'll hand it back over to you. You can continue.
Thank you. Here's a profile of the different layers in and around an ash pond. Free water is on top of the ash and is easiest to treat, and most likely requires only simple filtration. At the beginning of dewatering, the free water typically meets the discharge limits without additional treatment because the pond was designed to meet those limits. As the water is drawn down, the retention time in the pond is reduced and treatment is required. Poor and interstitial water is in contact with the ash and can contain contaminants that require co-precipitation or other means for removal in order to meet discharge requirements. Once this portion of the pond is disturbed, inlet water characteristics can change quickly, and the system needs to react to those changes. Groundwater from extraction wells and leachate can be low in TSS, but if this water was in contact with ash, it could require similar treatments as interstitial water in regards to the specific contaminants. Co-precipitation or reactive medias can be used to target these contaminants. There are several unique considerations in the design of ash pond treatment. First, timing. How long will the pond closure take? Size the system to match the schedule. Also, ensure that it can overcome setbacks from rainfall collecting in the drainage area. Public involvement should be expected and can cause delays, so seeking state approval before you mobilize your system is critical. The location. The ponds are not conveniently located to plant infrastructure. Some compromise with regard to the distance from plant infrastructure and utilities is needed to provide proper support for the treatment system. The use of diesel-powered pumps and generators are quicker to set up than a dedicated electrical service. But on the other hand, running an electrical service eliminates the need for fuel and is more reliable and could save money on longer-term projects. Potable water is hard to come by in most remote locations, but is needed for safety showers and mixing chemicals. So if it is not available, a smaller treatment system or storage for these needs is required. Meeting the outfall limits is the greatest concern of any of these projects. Typical historical limits are not challenging targets to meet with temporary systems, but some states have tightened limits for ash pond dewatering, and the system must be conservatively designed to always meet these limits. Lastly, the inlet water quality will change over the course of the project. Since the ash and water in the pond is not uniform, and the closure construction activities disturb the ash, both have an impact on the influent characteristics. Placing the pumps pulling the water out of the pond is important to prevent the feed water from changing, and keeping the pump in a location that's not affected by the daily closure activities is also important. The variables for pond closure are much the same as for any wastewater treatment application. Water quality in and out, as dictated by the local NPDES permit, volume to be evacuated, flow rate is affected by the time frame of the project. All discharge waters will have to meet pH, TSS, and oil and grease limits as a minimum. So moving left to right on the table, the system design moves from simple free water treatment that is easily clarified and filtered with typical mobile equipment to tighter design requirements for metals and nutrient removal, where more extensive treatment is required. Activated medias, wastewater ion exchange, and fine filtration all may be required to meet these limits. Here is a chart for the relative loading rates of various solid removal technologies. Moving from left to right, the loading rate increases based on the ability of the system to settle flock particles against the upward rising water flow. As the loading rate increases, the footprint of the equipment can be reduced while the capacity of the system is maintained. Equipment footprint is a key cost driver for temporary systems. Reducing the footprint makes mobilization of the equipment to remote locations easier while lowering cost. Ballasted flocculation with magnetite can achieve some of the highest loading rates for clarification technologies. Ballasted flocculation is the process of adding a heavy material to flock particles in order to increase the settling speed. Somewhat like a high molecular weight polymer that is used to grow flock mass and increase settling. A ballast material greatly increases the specific gravity of flock. In the past, ballast materials like clay and sand have been used, but now magnetite has been employed. Magnetite has three characteristics that make it an excellent choice for ballast material. First, it has a very high specific gravity, thus a high rise rate can be achieved. Next, it is magnetic, so after it has settled the flock, it can be easily separated by a magnet and recovered back to the front of the process. Lastly, it is not expensive. The ballasted flocculation process includes three key components. Part A, the reaction chamber where the chemicals and ballast are added. B, the settling clarifier where solids are separated by gravity. And C, the ballast recovery where the solids are separated from the ballast with a magnet, and the ballast is recycled and the solids are discharged. Since ash pond closure projects have some unique constraints, such as finite need, once the pond is closed, the system is not required, remote locations, and high treatment volumes, some traditional technologies are poor fits for the project requirements. The mobile ballasted COMAG process helps meet these unique requirements. In a mobile package design, the technology can deliver up to 1,500 GPM of treatment on a single semi-trailer footprint. The system is pre-plumbed and wired so that only minimal setup is required. When selecting a chemical treatment solution, co-precipitation of some ions can be achieved by ballasted clarification. Depending on the outfall limits, this can be an effective means to reduce dissolved ionic contaminants to an acceptable limit. Arsenic and zinc are two elements that show an over 90% removal rate by co-precipitation. Removal by this method can eliminate the need for a polishing technology. Here's a process flow diagram of a typical ash pond treatment system with two mobile clarifiers, and it is rated at 3,000 GPM. The first step of the system is the equalization tank that allows water from different ponds or different areas of the pond to be transferred to the system. This also allows the treatment waste streams to be recycled, increasing the overall recovery of the system. Finally, clear wells are used to check the effluent quality of the system before discharge. An example of a sludge handling system is also shown for the disposal of dry solids. In most cases, the dewatering of dry solids is only required at the tail end of pond closure, when there is no longer a place to dispose of the wet solid. A system similar to the one shown in the process flow diagram was used to dewater ash at a closed power plant. Because the plant demolition was already underway, utilities and support infrastructure were limited and factored greatly into the execution of the system design. The system uses co-precipitation to meet a zinc and arsenic outfall limit. Another example system is a 250-gallon-a-minute system that uses a reactive media technology called poronics for selenium removal. Here, the selenium limit could not be met by co-precipitation alone. Thus, clarification and reverse osmosis are used to concentrate the selenium before the reactive media system. Concentration in this fashion reduces the footprint of the poronic system by 4 times. Now I'd like to turn the presentation over to Charles McCloskey for the second half of our discussion. Thank you for your interest, and now Charles.
Thank you, Max. Yes, what we'd like to take a look at now is for operating steam plants. What is the impact of closing the ash basin before and after? So why would an existing operating steam plant close their ash basin? Some of the key criteria is the basin lined or unlined. All unlined basins will need to be closed. In addition, what is the condition of the liner, berms, or dams? What is the proximity to waterways, habitats, and communities? Has there been any seepage or outleakage affecting groundwater? And what is the overall short and long-term liability of maintaining the ash basin? A typical plant water balance prior to the ELG regulations and CCR regulations looks something like this. The primary purpose of the ash basin was for the transport and settling of bottom ash and fly ash. With the implementation of the ELG regulations, fly ash and bottom ash could no longer be sent to the ash basin and needed to be handled by dry ash handling or a closed loop system. What happens to the remaining flows when the ash basin is closed and the ash basin goes away? A new plant water balance might take a shape of something like this. The ELG requires specific guidelines for FGD purge water, and an FGD purge system and polish system may be required to meet these new limits. The remaining streams may be handled individually or combined as low-volume waste. The overall process of establishing the new plant water balance is often called redirection. When we talk about low-volume waste, we're not talking necessarily about low flows. We've seen flows as high as 8,000 GPM in the low-volume waste treatment system. The low-volume waste treatment system will capture all of the remaining streams that used to go to the ash basin. Coal pile runoff, process water from the plant makeup system, stormwater, seal water, boiler and cooling tower blowdown, boiler cleaning, and miscellaneous wastewaters. The basic treatment required will be TSS removal and pH adjustment and oil and grease removal. And depending on the unique effluent requirements of the site, some metals removal might also be required. The treatment options are settling basins, traditional clarifiers, or ballasted flocculation. Again, ballasted flocculation is an important tool in clarifying this water. As Max indicated, several ballasts have been used in the past, but most recently magnetite has been used because it has a higher specific gravity, resulting in a faster settling rate. This means higher rise rates, smaller footprints, and lower installation cost. In addition to the mobile system that Max showed earlier, there are also field-erected and skid-mounted systems that can be matched to the individual flows of any of the treatment streams or the overall low-volume waste treatment system. Now I'd like to take a look at a specific stream that may require a specific individual attention. This is the non-chemical boiler cleaning wastewater. This is the wastewater that is generated when the back end of the boiler is periodically cleaned during outages. This is usually high-pressure water blasting around the firebox, the air preheaters, the economizer, and even the electrostatic precipitator. This waste stream is characterized by high flow rates for a short duration. These outages usually only last for 3 to 10 days. The solids that are generated can be quite high. We've seen up to 20% TSS loading in these water streams. Depending on the type of coal, the pH can be very, very low or very, very high and require pH adjustment prior to discharge. And there will also be dissolved metals in this waste, most notably iron. The ELG limit reserved specifications for treating this water, but did say that nothing less than the best available technology should be used, and that must meet the local NEPIDES permit. If it's directed to the low-volume waste system, it could have an immediate effect if the system is undersized, or the low-volume waste system would need to be oversized to handle this periodic waste stream. Another option is to deal with this waste stream as a temporary system during the individual outages. This is what a typical flow diagram might look for a temporary system to handle non-chemical boiler cleaning wastewater. Let's look at each step. Settling would be very important. Flows up to 2,000 GPM and high solids, this is where initial pH adjustment would occur. To get good settling in this step, rise rates of less than 1 GPM per square foot need to be accomplished. And constant sludge takeoff has to be accomplished to sludge dewatering, or the settling tank will be overwhelmed. Options for settling include an existing basin, lake tank, weir tanks, or thickeners. The next step is clarification. The flow goes forward. The TSS is reduced from the very high level in the percent basis down to about 2,000 ppm. This is the place for the next step in pH adjustment, coagulation and flocculation, and removal of the fine solids down to the single digits of NTUs or ppm. The sludge dewatering step is key. Flow has to be taken off the settling step and the clarifiers to main forward flow. 1 to 3% solids is typical off of the clarifier. Thickened in a dewatering step, thickened up to 25 to 25% solids, and then further dewatered up to 25 to 50% solids. You need to calculate the tons per day of solids that will be generated, tons per hour, so that the dewatering system can be sized correctly. Plate and frame filter presses, belt filter presses, centrifuges, or geotubes are all options for accomplishing sludge dewatering such that the solids can be safely disposed of in an on-site or off-site landfill. I would like to turn it over to Aaron to ask the next poll question.
All right. Our next poll question is, how will the key dates for CCR ELG regulations affect when you need to stop using your ash pond?
Aaron, you should be on poll question number 2. I'm sorry.
I'm sorry, I missed the number. Okay. When are you planning your next non-chemical boiler cleaning application? So there's 3 choices here: within the next 6 months, greater than 6 months, or it's not applicable for some attendees. So the question should be out there, and attendees can answer at any time. Looks like a lot of attendees, the question isn't applicable. They're not doing non-chemical boiler cleaning. But for the remainder, it looks like the greater than 6 months is more prominent, but a few within the next 6 months.
Very good. Thank you. Thank you for responding. Let's take a look at a couple of case histories. The first case history occurs at a plant that has the advantage of an existing settling basin. They also have an on-site clarifier rated at 200 GPM. But during the boiler cleaning process, the flow surges to over 900 GPM. The plant is burning Illinois Basin coal and requires pH adjustment with lime to achieve proper pH for discharge. The plant has 2 outages, one for each unit, 5 to 10 days apart, once every year. The turbidity surges during this outage up to 1,200 NTUs. We supply this customer with a mobile clarifier that reduces the turbidity down to 10 NTUs and a total iron down to less than 1 ppm. This is an existing customer that has used this process every year for the last 5 years with a successful application. Let's take a look at another case history. This particular location did not have the advantage of a settling basin, so a bank of weir tanks were installed to provide initial settling. After settling, the settled water went forward to mobile clarifiers. The design flow was up to 2,000 GPM, so 2 mobile clarifiers were supplied. Due to very tight regulations on dissolved iron, or total iron, in the discharge, final filtration was added after the clarifiers. Sludge dewatering was attempted with lined filter boxes. This application occurred over 5 days, a very short period of time, and was focused on the air preheaters. Flows surged up to 2,000 GPM, and the turbidity, surged up to 2,200 NTU. The turbidity was reduced in the settling step down to about 450 NTU. Out of the clarifiers, 10 NTU, and out of the final effluent, less than 5 NTU. The iron results are shown on the bottom graph and were dramatically below 1 ppm for the entire outage, except for one filter change-out period when it just hit the upper limit of 1 ppm. Lessons learned during this application were, one, is that you can get very uneven flow during the water blasting. Working with the contractor to even out flow and create some surge capacity is the key to maintaining good performance in the settling step and the clarifier. Rapid settling can occur in whatever settling step you have. In this instance, it was the weir tanks. So with rapid settling, efficient sludge takeoff is required to maintain the settling performance. Secondly, finally, it took a long time to dewatering in the line filter boxes. We decided this was not the optimal design for an efficient dewatering of the solids. It really becomes a question of mass balance. So when you're taking a look at a particular application, you should look at the flow, the percent solids, and the pounds per day in cubic feet of sludge that will be generated. You must size the sludge dewatering system to be able to handle this very high amount of sludge in a very short period of time. Some options that are being investigated to increase sludge handling in a short period of time are mobile centrifuges and belt filter presses. If more space is available, we could also consider dewatering with geotubes. For higher volumes and sludge capacities, we're also looking at larger settling tanks, such as a lake tank. Whether you're looking for an ash basin closure, design of a low-volume waste system, or a temporary non-chemical boiler cleaning wastewater treatment system, the steps are very similar. Good analytical data collection, which can sometimes be quite difficult if it's an intermittent or uneven waste stream that you're dealing with. Timing, counting back from the compliance date. When will you need to have the system up and running, tested, and working before compliance is required? A good plan of attack with engineering and design of all key components. Identifying the key components that may be required, either capital, mobile, or ancillary equipment. And then execution with a trusted partner. For more information on our solutions for coal-fired power plants, or to get in contact with either Max or I, please contact us via this website or our email addresses. Thank you again for your attendance. And I'll turn it back to Aaron for the Q&A session.
All right, thank you, Charles. I'd like to thank both you and Max for providing such an informative and interesting presentation. While you were speaking, we've had a number of questions come in from the audience, and at this time we'll try to consolidate similar questions and answer as many as possible in the time remaining. Any questions that are not able to be answered at this time due to time constraints will be answered individually via email following the program. So one of the first questions I'll bring up is what opportunities for on-site water recycling rather than discharge do you typically see? And kind of follow up to that, is reuse usually not deemed cost effective?
Aaron, this is Max. I'll go ahead and field that one for you. It's a question of logistics and infrastructure mainly. When you look at the high volume that usually gets treated with an ash pond, for instance, you want to close the ash pond most likely as soon as possible, so you're going to treat a high volume of water. The plant water balance may not be able, you might be able to save some of that water, but there's most likely not a large need for that volume of water in the plant. And then getting that water to the process to can accept it can be challenging just from the infrastructure of the plant design. So there are opportunities, but there can be challenges to it, and we'd be glad to look at any opportunities that you might have.
All right, thanks, Max. How does the COMAG removal efficiency change for arsenic at concentrations greater than 50 parts per billion, say, for example, at a 500 part per billion concentration? Max, can you take that one too, or?
Yeah, that feeds into the topics that I was discussing. When you're talking about using co-precipitation to remove a particular element, you're looking at how that chemistry reacts, and then basically the pH and solubility of that element in order to get the removal efficiency. So you're going to do some jar testing and trial and error of your chemicals that you're going to apply to figure out what gets the best removal for you, and then execute that within the full-scale system. So we would take that water sample, test it in the lab, and then work to repeat those results in the field. To my knowledge, and Chuck, you might know of another, I think 300 ppb might have been close to the highest arsenic limit we've seen on an ash pond, and we were able to treat that to the outfall limit with co-precipitation. So that's another thing that factors into the ability for co-precipitation to work, is what the, you're talking about a percent removal. So if you can get a large enough percent removal, it depends somewhat on your starting position. Chuck, did you have any comment for that?
Yeah, I would just add that it depends. Arsenic removal, it depends on the state of the arsenic, the specific valence of the arsenic, and then it's highly dependent upon the amount of coagulant that you add. So if you can add more and more coagulant, ferrous or ferric chloride, to drive that reaction. But as Max said, it's dependent upon good upfront evaluation and testing prior to initiation.
All right. Thank you both. Here's another question. Can Evoqua water treatment systems be expanded to dewater impoundment, and they list 8,000 gallon per minute, and meet NPDES permit limits for 8,000 gallon per minute systems? And then a follow-on to that is, what would be the monthly estimated cost for rental or water treatment equipment?
I can handle that question. It's simple answer is yes, we'd love to look at that opportunity with you to discuss the cost and et cetera. Would be outside the scope of the conversation here, but it certainly looks and sounds like systems that we've proposed and jobs we've executed. So that to the first part is, can we do that? Yes. And to the second part on cost, it depends.
All right, and that makes sense. I'm sure every situation is different, and the needs would all be different. So another question, can you further explain the process for heavy metals such as selenium removal?
Charles, I'll let you take that one.
Yeah, for selenium removal, what we are using a non-biological approach, a physical-chemical approach, using what's known as hybrid zero-valent iron, and it's known as our Poronox process. All selenium removal takes time, so in order to reduce the footprint of the selenium removal step, where applicable, we use filtration and RO to concentrate up the selenium waste to reduce the size and footprint of the selenium removal step. But our process of zero-valent iron has proved very effective in a non-biological system for reducing selenium from the single ppm level down to acceptable limits.
All right, thanks, Charles. Another question here. What infrastructure requirements are needed to support the portable unit, such as how many megawatts or what kind of water supply, et cetera?
I'll take that. The clarification equipment, we've got pumps to move the water from collection tanks and clear wells, and so that's the majority of the electrical requirement. Depending on the size of the system, maybe a couple of hundred amps of 480 powers required, and then maybe moving up to 1,000 for a significantly larger system. The infrastructure for moving the water from one location to the other is all piping. We're typically handling that with HDPE that is constructed on site, so that some of the jobs that scope is relatively small, and others just finding a location for the treatment system in and amongst the various different pond locations can create some extensive pipe runs, but that's not that difficult.
Yeah, I'm sure.
It's just fused together and lays on the ground.
Right. All right. Another question from an attendee here. Can the magnetite media result in higher iron levels in the clarifier effluent due to carryover?
Charles, I'll let you take that one.
Yeah, that's another unique property of magnetite, and really another important criteria for choosing a ballast is that the ballast itself is inert to the process. It's simply a weight, and as long as the pH is controlled in the proper range, there's no dissolution of the ballast or no carryover that occurs. The ballast is so heavy that it settles quite well in the clarifier, and there's no dissolution or impact on effluent iron concentration.
All right. Thank you, Charles. Here's one. Does Evoqua furnish, erect, demobilize, and operate the temporary systems?
Yes, good question. We work with the customer in delivering what they would like us to do. So there are jobs where we do a large portion of that scope, and then there's other jobs where the customer will execute that. But we like to interconnect our own equipment, et cetera, so that it kind of cuts down on communication for with contractors and subcontractors. So our position is to do as much of that scope fits our abilities.
All right. Thank you, Max. What are the possible sources of arsenic contamination in groundwater? Is it due to leaching of fertilizers, et cetera, or due to oxidation of arsenopyrites? Who's best able to handle that question?
Charles, you want to take a stab at that?
Yeah, I would hope that for any given situation that the ash basin is contained, that monitoring wells are in place to make sure that there's no out leakage, and if necessary, any extraction wells are in place to create a barrier to prevent the out leakage from any arsenic into the groundwater. Any arsenic that comes from other sources is beyond the scope of this discussion, but we know that landfill leachate can be treated successfully, and good containment of the ash basin water and treatment of the ash basin water will prevent the arsenic from getting into the environment.
All right, thank you. This one is again about costs, but it may be something that can be answered here. Are costs fixed for use or based on processing volumes? How do you basically figure that out?
We typically like a model that is a fixed cost that the customer, this kind of gets into how the contracts are presented to customers to meet their needs. But I'd say the most popular selection is for a fixed cost. But within that, it contains a availability and a production process guarantee. So you're receiving a volume for that cost. It's just not necessarily line itemed out on a per gallon basis. So I would say for the most often selected or the preferred way for the contract to be put together is on a fixed cost basis.
Okay. Is the flock a hazardous waste when disposed? What is the typical concentration of arsenic?
Go ahead, Chuck.
This is Chuck. Yeah, we've tested the flock off of ballasted flocculation clarifiers in a number of applications, both for non-chemical boiler cleaning wastewater as well as coal ash basin dewatering. And we found that the sludge passes the T-clip test in that there's no redissolution of the arsenic or release of the arsenic or other heavy metals from the sludge. The exact concentration will depend on the water going into the process itself, but suffice to say that the sludge has proved to be non-hazardous for disposal in either an on-site or off-site landfill.
All right. Can you correlate the TSS to NTUs? For example, how much TSS in milligrams per liter is 10 NTU?
I can take that one. So what we'll typically do to help monitor the system is use a turbidity meter to check the effluent of the treatment system, and then build a correlation between the two that it typically is adjusted by that site correlation, but we're seeing 10 NTU would probably be somewhere in the 20 to 30 ppm TSS. So we're constantly monitoring the turbidity versus TSS correlation and adjusting the turbidity meter limit to give us some cushion against the TSS outfall requirements. And then, basically by spot checking TSS on up to a daily basis and correlating that data back together.
All right. Can the ballasted flocculation clarifier replace a standard clarifier? And he gives a question here, looking to remove hardness in well water for cycling up a cooling tower. This is a wholly non-chemical process, correct? And that's a question. To start with, can the ballasted flocculation clarifier replace a standard clarifier?
Well, that's the easy
most
one.
Definitely.
Go ahead, Charles.
Yeah, I was going to say most definitely. I'm not sure I understood the second part of the question.
They're looking to remove hardness in well water and cycling up a cooling tower.
Hardness removal is generally accomplished through cold lime or cold lime soda softening. So it is a chemical process to remove hardness if you're using a clarifier.
Okay. All right. Do you have real-time monitoring for customers of water reduction rates?
Yes, the Evoqua has a system called Link to Site, which records the operation and the instrument data for us, and that can be set up for remote monitoring in real time.
All right. Has anyone considered using a compaction screw system for dewatering? Have you ever seen that done?
Chuck, you want to take a stab at that?
We have not, but we are looking for, and we would be interested to learn more. With the high volume of sludge created, particularly during the non-chemical boiler cleaning wash process, we are looking for alternatives for faster and more efficient means of dewatering a high amount of sludge over a short period of time. So we'd be interested to learn more.
All right. How much space is required for a 4,000 to 8,000 gallon per minute treatment system?
I might just happen to know the answer to that. It's probably somewhere between 100 to 150 feet on length and maybe about 200 foot width. So the lay of the land might factor in a little bit. The clarification technology needs a fairly flat surface because its operation is under gravity, so you have to be mindful of that. But that's kind of the ballpark of the system area.
All right. How do you account for a site being a zero discharge facility?
If that's related to ash pond closure or non-chemical boiler cleaning, might kind of be important.
Okay. I mean, I'm sure you work with zero discharge facilities, and you must find a way to deal with it one way or another, I guess, huh?
Right. I guess I can speak to on an ash pond basis. A number of coal plants have ash ponds that, due to the heat load from the unit operating, maintain an evaporation rate on the pond that keeps water from flowing out of the pond. So with the ash pond closing, you have to eliminate that water. It probably goes beyond the scope of the way we described pond closure today, but I have looked at and investigated sites that have that unique characteristic, and the system can be designed for that. It gets when you get to concentrating the volume, you need to start looking at kind of what you do with the last several percent of the water, but a process can be developed.
All right. What is cycle time on filter press with boiler cleanup water?
Typically, it depends on the coal that's being burned. With the high pH coal from Powder River Basin, it can be as short as 1 hour. For Illinois coal or bituminous coal, it can be as high as 3 hours. So that's one of the limitations on a plate and frame filter press is the number of presses needed to achieve the dewatering of the sludge in a short period of time.
All right. And follow up on that, why use a batch process for a high flow stream?
Yeah, that's why we are looking at alternatives such as centrifuges and belt filter presses, again, because of the high volume of waste in a very short period of time.
Okay. You mentioned pyronics. What exactly is that and how does it work? Chuck, is that something you would answer?
Yeah, pyronics, again, is our trade name for hybrid zero-valent iron. Zero-valent iron has been known for some time to be an effective reducing and precipitation agent for selenium. The key to pyronics is maintaining its efficacy, preventing it from rusting, and maintaining it in an active state so it continues to work over a long period of time. But it's zero-valent iron that tends to reduce selenate to selenite or elemental selenium, and then precipitates and absorbs selenium so it can be removed from the water stream and concentrated and disposed of as a solid.
All right. Next question, how do you decide which treatment process is best for a particular ash pond? What sort of decision process goes into that?
I'd say the most important thing is the NPDES permit for the particular pond, and then any changes or considerations. I've seen normal operation of ash ponds be governed under a particular permit, and then dewatering be operated under a stricter permit. So that's your target for your design, and then of course your inlet starting water will determine it.
All right. If a mobile treatment system is installed, who operates the system and how much input is needed from the plant?
I'll take that one. Evoqua would typically operate these systems, perform all the maintenance and operation, quality checks, etc. for the customer, interface with them as far as their demands and for volume reduction, interfacing with construction activities to dewater certain areas at certain times, to be flexible to manage that treatment process in order for the closure activities to continue to take place in and around the closure process. So we have a core of operators that we dispatch to the sites and work with our customers to provide the treatment to meet their needs.
Okay. Thanks, Max. Along the same lines about temporary systems, do the temporary treatment systems include a performance guarantee?
I'll take that one again. I mentioned earlier, yes, that the contracts are usually set up with a volume and quality. Of course, the quality being the governing permit, and some buffer between the outfall limit and what we'd call a divert or trip point limit, so that that's always lower than the outfall requirement.
All right. Thanks, Max. I guess we're coming up on the end of the program here. So as I mentioned, any questions that we didn't get to will be answered individually via email. Again, I'd like to thank Evoqua Water Technologies for underwriting today's event. and I'd like to thank all attendees for joining us. We hope you found today's presentation beneficial, and I hope you have a great day. Chuck and Max, thank you very much, and with that, we'll sign off.